Today's learning target. I can determine the end behavior of any function. And we kind of did this a little bit in pre-calc. This is one of the few concepts. There's a lot of content that carries over from pre-calc. Like you need the factoring, working with quadratics, polynomials. That content carries over. But there's few concepts that you reuse. This is one of them, and it's actually pretty easy. All right? So, let's talk about an end behavior. Okay? An end behavior, and I'm just going to draw this little sketch here that you don't have to draw. You can just look up here. When I have this set of axes here, and I have a function or a graph on it, let's say we have something that looks like this. It goes up forever, comes down, does a little dance thing here. Who knows this little dip thing? I don't know. It goes back up here. All right? I might have another function where the ends model or behave the exact same. Which means, what if I had a parabola? Went like this, came back up. Over here, it's obviously very, very different here. But as this thing goes to the right forever, it acts the same. As this thing goes to the left forever, it acts the same. So when they talk about end behavior, that's what they're talking about. When it goes to the right forever, the right's end forever, the left end forever. And we can determine that very easily. Of course, it'll seem complicated at first. And then when I break it down, you're like, oh, that's really this stuff? Yes. Yes. A function, G, is a right behavior model for F. Another function F. If and only if the limit of f of x divided by g of x as x approaches infinity is equal to 1. And as we start plugging actual polynomials into these, some of you are going to think, oh, I remember that from pre-calc. That really wasn't that bad. And it is not. Okay? So, if I divide my two functions here, and I take the limit as x approaches infinity, that means that it equals 1. That means they are the same in behavior, which means g of x would be a right behavior model for what f of x is. No. And if there's a right behavior model, there's also a left behavior model. Okay. If and only if, well, it's the same situation, but your limit is x approaches negative infinity. Because on the left side, isn't that where x goes to negative infinity? Right. And the right side is where x goes to positive infinity. So that's why we use those. So now, let's take a look, shall we? Let f of x equal 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. All right? And let g of x equal 3x to the fourth. Show that while f and g are quite different numerically for small values of x, that means closer to the origin, that they are virtually identical for larger values of x. That's all this means, okay? Whether it's positive or negative infinity for large values of x. All right? So, we just learned something, kids, didn't we? If it is a right behavior model, that means I'm going to take a limit as x approaches infinity of f of x over g of x, correct? Which would mean 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6 all over 3x to the fourth. Now, if it is a right behavior model, that should equal 1. This should equal 1. And let's check it out, shall we? Well, that's a good question. The question was, how do we know whether this is negative or positive infinity? All right, I'm choosing right. I've got to check right and left. Okay, if I'm choosing right, right has the positive infinity. Okay, and if you're going to check left, which we'll check next, that should have the negative infinity. So let's do this. Anyone in pre-calc remember anytime I put an infinity in, what I'm supposed to do? Do small values matter if you put infinity in? Like if I have infinity plus 1, does a plus 1 matter? So do you remember what I do? Whenever I plug an infinity in for x, I keep the biggest term on the top and the biggest term on the bottom. I simplify them as much as possible, and then if there's still any x's remaining, I put infinity in for it. So I've got 3x to the 4th over 3x to the 4th. Okay, what does that reduce to? There's no place, if this is my limit, there's no place, there's no x here to put the infinity into. We're good. We're good to go. So that is equal 1. So this function, g of x, acts identical. It's a behavioral model for the right side of this whole function here. Like, I don't know what that function does in the middle. But I know as it goes to the right forever, it's going to act just like 3x to the 4th. All right, let's check the left side, children. Oh, I am so lazy, and I can't copy and paste that. Left side, it's the limit as x approaches negative infinity of the same fraction. 3x to the 4th minus 2x cubed plus 3x squared minus 5x plus 6 all over 3x to the 4th. I need to see if that equals 1. It's not negative 1. The only difference is my infinity is negative. They should still both equal 1. And we do pretty much the same thing. If my x value is approaching positive or negative infinity, I keep the biggest term on the top, and I keep the biggest term on the bottom. So I have 3x to the 4th over 3x to the 4th. Anything over itself is 1. Boom. It doesn't matter. But Visco, what about as x approaches negative? There's no x anymore in here to put the negative infinity into. So it's 1. So now, g of x is a perfect model both to the left and right side of what our f of x function would behave or how it would look. So, do you want to see this on a calculator? The biggest term. The biggest term is the one with the biggest exponent. Well, if they write it in proper format, the biggest exponent should be first. But sometimes they might switch it and not write it in proper format. It's up to you to recognize it. But the biggest term is always the one that has the biggest exponent with the variable. All right? So, for poops and giggles, let's take a look at this, shall we? Okay, I want to have one of you guys read off to me when I'm ready. What's that first one? It's 3x to the 4th minus 2x cubed plus 3x squared. Okay. Minus 5x plus 6. And then I have just 3x to the 4th. Now the middle, as it's close to the origin, they're not going to be the same. But as it goes to the right forever and to the left forever, they should look the same. So why don't we do this? We'll make this the thicker line. Okay. And let's start our window from -5. Yep, that would be nice. From -5 to 5. And we'll do the same thing here. -5 to 5. So if I graph this, yay, there's my first one. And there's my second one. That is definitely not the same. Okay? So let's zoom out. Bam. Ooh. There it is. And there it is. Starting to look like it's right on there. If I zoomed out again, it would look even more, but then the thick line would totally encompass the small line. You really wouldn't see it. You won't see it there. But the further and further and further you back out, there was the first one, and then the second one's just going to go right over it. Bam. See that? They look exactly the same. But if I zoom in really, really close, they don't look the same at all. That's all it's saying. That's all it's telling you. All right? So now that we know some of the math behind proving whether something is a behavioral model, or the left or right behavioral model, now we're going to see if we can come up with one ourselves, okay? Or prove that what they give us, is an actual model. So let's take a look. Let f of x be this function here, x plus e to the x. All right? Show that g of x equals x is a right end behavior model for f. All right? That's the first thing. That's the right end behavior. And it's saying, while h of x, which is this e to the negative x, is a left behavior model. So we got to prove the right and left. And they're two different functions. That's okay. One will be a right behavior model. One will be a left behavior model. How do I do the right?
Positive.
It's the limits as x goes to positive infinity. Now, which are the two functions? X plus e to the negative x, because I want f of x over g of x. I want f of x over g of x. All over x, and that should equal 1. They want me to prove that. All right, well, here's something that comes really handy in calculus. I'm going to break this up right here. Okay, I'm going to break this up. I'm going to say that's x over x plus e to the negative x over x. You see how I can do that, right? Because if I added those two the same, wouldn't the bottom stay the same? Will stay x, yeah. And I get x plus e to the negative x. Now, I'm going to take the limits as x approaches infinity of that. Well, what is x over x?
1.
1 plus e to the negative x over x. I'm still taking the limits as x approaches infinity. Okay. So what do? Well, yeah, there's nothing else that I can do here. If I wanted to, I can simplify. What do I do with negative exponents? I flip negative exponents to make them positive, right? So that's really 1 plus, this is 1 e to the x. It's going to be 1, and my e to the x is just going to come to the bottom, and now it's positive. I've got to throw an infinity in for both of those x's. So if I do that, I got 1 plus 1 over basically infinity. What does 1 over infinity approach?
0.
Because the bottom fraction gets bigger and bigger, the value of that fraction gets smaller and smaller and smaller. So much so that it looks like 0, and oh my God, it equals 1, doesn't it? It equals 1. Now I have to do the same thing for the left side. I do the same thing for the left side. Nice. Now, what do we got? H of x. The left side is the limits as x approaches negative infinity of f of x over h of x, because we're testing h of x now for the left side. So I've got x plus e to the negative x all over e to the negative x. That should equal 1 if that is a left behavior. We're doing the same thing. We're going to break this up into two fractions. So ready? Okay, so this is going to be x over e to the negative x plus e to the negative x over e to the negative x. Yeah, so now this is going to be x over e to the negative x plus 1, isn't it? And we still need to plug in our infinity for x. So let's do that. We have infinity. Well, here's what we need to do. We're not plugging in infinity anymore, are we?
Oh.
We're plugging in negative infinity. So I got negative infinity for my x over e to the negation of x, which is negative infinity, right? I just threw a negative infinity in here, plus 1. What happens when I negate a negative?
Positive.
So now I got negative infinity over e to the infinity. So you see why I didn't have to flip that? It stays down there when I negate a negative anyways. Plus 1. So technically, this should be 0 plus 1 equals 1, and it should work. Do you understand why this equals 0?
No.
I have an infinity on the top and the bottom, don't I? The infinity on the top is counting, well, by negative 1s, right? Negative 1, negative 2, negative 3. The infinity at the bottom, the number e is actually equal to 2. It's a 0.718 something. It's irrational. So it's 2.718 to the first. That's here. You see how that's bigger than 1? Then it's 2.78 squared. Well, 2 squared is 4. 3 squared is 9, so it's somewhere between 4 and 9. I don't know, it's called 6 something. Isn't that bigger than 2? Negative 2? The next one, it's cubed. Okay, that's 8 or 27. I don't know, let's call it 17. You see how this gets bigger and bigger on the bottom of the fraction at a quicker rate than the top of the fraction does? If the bottom of the fraction gets bigger at a faster rate, the overall value of the fraction gets closer and closer to 0. Does that make sense? The way I explained it?
Yeah.
You! Don't you just wake up? Come on. Let me explain it one more time with simple numbers that are not irrational, like e. Okay? So, for example, if I have infinity over 2 to the infinity, this will approach 0. How come? Because let's start plugging in numbers from infinity that get bigger, starting at 1. 1, 2, 3. If I plug in 1 for infinity, I have 1 over 2 to the 1, which is 1 half. Let's plug a 2 in for infinity. I got 2 over 2 squared. Oh my god, that's 1. Well, that's 2 over 4, which is 1 half, right? Let's plug in a 3. 3 over 2 cubed. That's 3 over 8. That's smaller than a half. This is 0.5. This is is it 375? I don't know, I might be wrong. Let's plug in 4. 4. Yeah. 4 and 2 to the 4th. That's 4 over 16. That's 0.25. You see how this number gets smaller and smaller? The bigger infinity gets, the smaller the value gets, because this number is getting larger at a faster rate than this number is. So it approaches 0. All right, so it's simple. All right? If I want to find just point blank, not the right end behavior, not the left end behavior, but just the end behavior model of a function, it is very simple. It's the term with the highest degree. It's your biggest term of the polynomial. So what does that mean? Well, we'll do an example down here, but let's fill in these other blanks first. Okay? If it's a fraction, take the highest degree of the numerator and the highest degree of the denominator, then simplify. It's just like when we plug in infinity, right? Don't we keep the highest term on top, the highest term on bottom? Okay? So for example, what is the end behavior model of the function f of x, which is 4x cubed minus 6x squared plus 15x minus 9? Is that a fraction? Is this a fraction? No, so you don't have to do this one. You just have to do this top one. What do? Take the term with the highest degree. What is it? Dozer. It's hot in here, I know. It's 4x cubed. There you go. That's the end behavior right there. This function, even though it does not look like this near the origin, as I back up farther and farther and farther away, they look identical. All right, they look identical. It's that simple. Yes, when you zoom out, it'll look identical, absolutely. All right? Here we go. Find the end behavior of this model. You should be able to tell this to me without really putting that much thought into it. What do I do first? Highest degree of the numerator, 2x to the fifth, over 3x squared. That's the highest degree in the denominator. Then I simplify that. What can I do here? Take what out?
Take square.
Take x squared out. Take 2x's from here, 2x's from here. So that it's 2/3 x cubed. This is the end behavior model of my function f of x. No, because when you put it in infinity, the smaller terms matter. No, if I add 1 to infinity, what's the big deal? I don't care. I got infinity dollars. You're gonna give me a dollar. What do you think I'm gonna do with it? Sneeze in it and give it back to you because I don't need it. Okay. Someone's blowing their nose. That's all. There it is. All right. Let's try. Oh, she said wait. All right, how about, Sienna, can you tell me what the end behavior model for this is? It's 2/5, absolutely. Why? Because I take biggest term at the top, biggest term at the bottom. This doesn't matter. And I simplify it. Well, I can actually cancel out my x cubed, so it's 2/5. The line, y equals 2/5, is a horizontal line on the graph that touches 2/5 on the y-axis, doesn't it? That means if this will be right at 2/5 on the y. That means this whole thing that I started with, this whole thing right here that I started with, I don't know, might do something funky in the middle, blah, 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 but then as it goes out to the end, it looks like that, and it kind of goes out like that, and if you back up far enough away, it looks like a horizontal line. You're welcome. One thing that is not on these notes that might be on the homework, because I did it like a week and a half. Do you notice about the right and left here? They might give you a function, f of x, and they might ask you to find out what function would be the left behavior versus the right behavior. That means you got to try and find like what g of x would be in h of x. They won't give it to you. But take a look at this. Look what I did here. I broke it up, correct? And what happened to one of my fractions? It turned into 1, didn't it? Look what I did here. I broke it up, and look what happened to one of my fractions. It became 1. So chances are, it's either going to be x or e of x. Because when you break them up, one of them has got to match to become 1, doesn't it? 1 plus 0. Sometimes the same thing. Maybe x would have worked both, you know, like you might get x squared or whatever. But just pick one of them and try it. If it doesn't work, pick the other one. Did everybody understand what I just said? So when you come in tomorrow, we're going to I don't get, how did you come up with x squared? I'm going to be like, because I had to pick either, like, if I have x squared plus e to the x, I'm either going to divide both of them by x squared so that this becomes 1, or I'm going to divide both of them by e to the x so that this becomes 1. One of them has to be 1 and the other one will go to 0. Remember, it has to equal 1, doesn't it?